Welcome to Chapter 3, Descriptive Statistics. In this chapter, we will explore one of the most important areas of statistics, describing and summarizing data. Before we can analyze data or make decisions, we must first understand what the data tell us. Descriptive statistics provide the tools needed to organize, summarize, and interpret information in a meaningful way. Imagine collecting hundreds or even thousands of observations. Looking at raw numbers alone can be overwhelming. Descriptive statistics transform those numbers into useful information by identifying patterns, trends, and relationships within the data. Throughout this chapter, we will study three major categories of descriptive statistics. Measures of central tendency, including the mean, median, and mode, which describe the center or typical value of a dataset. Measures of variation, including the range, variance, standard deviation, coefficient of variation, and Chebyshev's theorem, which measure how spread out the data are and help us evaluate consistency and variability. Measures of position, including percentiles, quartiles, deciles, z-scores, and box plots, which help determine the relative standing of individual observations within a dataset and identify unusual values or outliers. As we progress through this chapter, you will learn not only how to calculate these statistical measures, but also how to interpret them correctly and apply them to real-world situations. These concepts are widely used in education, business, healthcare, engineering, economics, finance, and scientific research to support data-driven decision-making. By the end of this chapter, you will be able to calculate and interpret measures of central tendency, measure and compare variability among datasets, determine the relative position of observations using percentiles, quartiles, deciles, and z-scores, identify outliers using box plots and the interquartile range, select the most appropriate statistical measure for different types of data, interpret statistical results, and communicate your findings with confidence. Descriptive statistics are the foundation of all statistical analysis. Mastering these concepts will prepare you for future topics such as probability, sampling distributions, confidence intervals, hypothesis testing, and regression analysis. I encourage you to work through every example, complete the practice problems, and focus on understanding the meaning behind each calculation, not simply memorizing formulas. Statistics is more than mathematics. It is a science of learning from data and making informed decisions. Let's begin our journey into Chapter 3, Descriptive Statistics, where numbers become meaningful information and data tell their story. Measures of central tendency provide a single value that represents an entire collection of data. The mean is commonly called the average and is the most frequently used measure of central tendency. Because every value contributes to mean, it is considered a very reliable measure. A single extremely large or small value can greatly affect the mean. Such values are called outliers. The median divides a dataset into two equal parts. When the number of observations is even, the median is the average of the two middle values. The median is often used for income and housing price data because extreme values do not distort it. The mode identifies the most common observation. Some data sets may have multiple values occurring with the same highest frequency. Different situations require different measures of central tendency. Weighted means are commonly used for course grades. The mid-range is easy to calculate, but is very sensitive to extreme values. Applications. Measures of central tendency are used in education, economics, healthcare, business, government. Examples include average salaries, test scores, and customer satisfaction ratings. Conclusion. In this section, we studied measures of central tendency. We learn how to calculate and interpret mean, median, mode, weighted mean, mid-range. These measures help summarize large amounts of data using a single representative value. In Section 3.2, we will study measures of variation, including range, variance, and standard deviation. Introduction. Welcome to Section 3.2 of Statistics. In Section 3.1, we learn how to describe the center of a dataset using the mean, median, and mode. However, two datasets can have the same mean and still be very different. Therefore, we need measures that describe how spread out the data are. In this section, we will study measures of variation, including the range, variance, and standard deviation. Measures of variation help us understand the consistency or variability of data. The range is the simplest measure of variation. The range depends only on the smallest and largest values and ignores all other observations. Variance tells us how much the data vary around the mean. Variance is expressed in squared units. Standard deviation is the square root of variance and is the most commonly used measure of variation. Interpreting standard deviation. Small standard deviation. Data clustered near the mean. Large standard deviation. Data spread far from mean. The standard deviation measures the typical distance of observations from the mean. Population formulas are used when data from the entire population are available. This rule helps us understand how data are distributed around the mean. Most observations are found close to the mean. Chebyshev's theorem. Definition. Chebyshev's theorem states that for any dataset, regardless of its shape, normal, skewed, or irregular, the proportion of observations that lie within k standard deviations of the mean is at least 1 minus 1 divided by k squared, where k greater than 1k equals number of standard deviations from mean. This theorem guarantees a minimum percentage of data within a certain distance from the mean. Chebyshev's theorem tells us the minimum proportion of data that must lie within a certain number of standard deviations of the mean, regardless of the shape of the distribution. For example, at least 75% of all observations lie within 2 standard deviations of the mean, and at least 88.89% lie within 3 standard deviations. This makes the theorem especially useful when the distribution is unknown or not normally distributed. The coefficient of variation compares variability between different datasets. Applications. Measures of variation are used in business, finance, education, medicine, scientific research. Understanding variation helps researchers evaluate risk, consistency, and reliability. Conclusion. In this chapter, we learned about measures of variation. We studied range of variance, standard deviation, empirical rule, coefficient of variation. These measures help us understand how data are spread around the mean. Welcome to our lesson on measures of position. In this section, we will learn how to determine the relative position of a data value within a data set. We will study percentiles, quartiles, deciles, z-scores, and how these measures are used to compare observations. These concepts are widely used in education, medicine, business, psychology, and many other fields. Learning objectives. After completing this lesson, students will be able to define measures of position, calculate percentiles, find quartiles, compute deciles, interpret z-scores, compare observations from different data sets, solve real-world applications. By the end of this lesson, you should understand the major measures of position used in statistics. You will know how to calculate and interpret percentiles, quartiles, deciles, and z-scores, and apply these concepts to practical situations. What are measures of position? Measures of position describe where an individual value lies relative to the other observations in a data set. Examples include percentiles, quartiles, deciles, standard scores, z-scores. Measures of position tell us the location of a data value. Compared to the rest of the data, rather than describing the center or spread, they indicate where an observation stands in the distribution. Percentiles are one of the most commonly used measures of position. If a student scores at the 80th percentile, that student performed as well as or better than 80% of all students. To locate a percentile, we first compute its position using this formula. Once the location is found, we determine whether interpolation is needed between two observations. The location of the 40th percentile is 4, a whole number. So, the answer is the average positions of 4th and 5th, which is open parenthesis 24 plus 27 close parenthesis, divided by 2, is equal to 25.5. Therefore, the 40th percentile is 25.5. Quartiles. Quartiles divide the data into 4 equal parts. Q1 equals 25th percentile. Q2 equals median. Q3 equals 75th percentile. Quartiles are special percentiles. The first quartile represents the lowest 25% of the data. The second quartile is a median, while the third quartile marks the point below which 75% of the observations lie. A box plot visually represents quartiles. The box contains the middle 50% of the data, while the whiskers extend toward the minimum and maximum observations. Deciles divide the data into 10 equal sections. They are frequently used in standardized testing and economic studies. The z-score measures how many standard deviations a value lies above or below the mean. Positive z-scores indicate values above the mean, while negative z-scores indicate values below it. This student performed exceptionally well. A z-score of 2 indicates that the score is 2 standard deviations higher than the average. Applications, college admissions, SAT scores, ACT scores, medical research, income distributions, employee evaluations. Measures of position are used extensively in education, healthcare, economics, psychology, and many other disciplines to compare individuals within a group. Pause the video and try to calculate the 3 quartiles. Use the percentile formula to locate the 75th percentile. Congratulations on completing Chapter 3, Descriptive Statistics. In this chapter, you learn the essential statistical tools used to summarize, describe, and interpret data. These concepts form the foundation for more advanced statistical methods and are widely used in business, healthcare, education, engineering, and scientific research. We began by studying measures of central tendency, including the mean, median, and mode. These measures help identify the center or typical value of a data set. Each measure has its own strengths. The mean uses every observation, the median is resistant to extreme values, and the mode identifies the most frequently occurring value. Next, we explore measures of variation, including the range, variance, standard deviation, and coefficient of variation. These measures tell us how spread out the data are around the center. Two data sets may have the same average, but very different amounts of variability. Understanding variation allows us to evaluate consistency, compare different data sets, and make more informed decisions. We also learn Chebyshev's theorem, which applies to any distribution regardless of its shape. This theorem helps estimate the minimum percentage of observations that fall within a specified number of standard deviations from a mean, making it especially useful when data are not normally distributed. Finally, we examine measures of position, including percentiles, quartiles, deciles, z-scores, and box plots. These tools allow us to determine where an individual observation lies relative to the rest of the data. Measures of position are valuable for ranking students, interpreting standardized test scores, identifying outliers, and comparing performances across different groups. Throughout this chapter, you also develop the ability to organize and summarize numerical data effectively, choose the most appropriate measure for different situations, interpret statistical results in meaningful contexts, compare distributions using both numerical measures and graphical displays, detect outliers and understand their effect on statistical summaries. Use technology such as calculators or statistical software to perform calculations accurately and efficiently. As you continue your study of statistics, remember that descriptive statistics do not make predictions or establish cause and effect relationships. Instead, they provide a clear and accurate summary of the data, allowing us to understand patterns before moving on to inferential statistics. In the next chapter, you will build upon these concepts by learning how probability and statistical inference enable us to draw conclusions about populations from sample data. Thank you for your hard work throughout this chapter. Review the concepts regularly, practice solving problems, and focus on understanding why each statistical measure is appropriate in different situations. A strong foundation in descriptive statistics will make the rest of the course much easier and will equip you with valuable analytical skills for your academic studies and future career. Keep practicing, stay curious, and remember, statistics is not just about numbers. It is about making informed decisions based on data. Chapter 4, Probability. Introduction. Welcome to Chapter 4, Statistics. Probability is the branch of mathematics that studies chance and uncertainty. It helps us predict how likely an event is to occur and forms a foundation of inferential statistics. In this chapter, we will learn how to calculate probabilities and apply them to real-life situations.
All right. Before we start, is there anything you need to ask me about what I covered last time? Okay. Let's talk about addition rule of probability. So I give you the formula. So if you have two events with the connective word or, the probability of A or B, A is an event, B is also an event. So to find the probability will be P of A plus P of B minus P of A and B. But if the two events are mutually exclusive, the probability of P of A or B will be just P of A plus P of B. You do not need the minus P of A and B. All right. So let's try this example here. Okay. Let's try this one.
Can I say it again? So
Hello?
I can take a picture.
Are you
Can I
talking to
see
me?
yes.
What did you say?
Can I see the slide, the first one, please?
I think you got this last time I asked you to copy that last time. Check your notes.
Okay.
Okay?
Okay.
Okay? Good. Now,
Yes.
let's try this one here. Solution to the blue. Yeah. Okay, so if a single die, okay, so talking about a single die, so the sample space will be 1, 2, 3, 4, 5, 6. Okay? Because a die has 6 faces. You're talking about even. So even, let's look for even number. That's 2, 4, 6. So n even equals 3. Got it? And then the second event is prime. So prime, looking for prime numbers, will be 2, 3, 5. So n prime got also 3 outcomes. Is this clear?
Yes.
Now, look at the two events. You got even, the outcomes are 2, 4, and 6. Prime, the outcomes are 2, 3, and 5. What do you observe? Do you think these two events have something in common?
Yeah.
What is this?
They both equal 3.
Not only look at the outcomes.
And they both have 2.
Yes. So these two events are not mutually exclusive because they have a number 2 in common. So therefore, we're going to put even and prime will be just 2. Make sense?
Yes.
And then n even, and prime, I'm going to use E for event. I'm gonna use E for event and then P for prime, okay? So E even and prime will be just one because there's only one outcome. Got it?
Yes.
Now you're going to apply the addition rule of probability. Probability. Okay? So recall P of A or B equals P of A plus P of B minus P of A and B. Now, you're going to replace A with even or E, and then replace B with prime or P. P of even, E for even, or prime would be P of even plus P of prime minus P of even and prime. Is this clear? Yes? No.
Yes.
Now,
Mm-hmm.
now, so N P of A will be N of E over N of S plus P of prime would be N of P over N of S minus P of A and P would be N of E and P over N of S. Now, N of E is 3, N of S is 6. That's 3 over 6. And then N of E and E will be 1. That's 1 over 6. So P of even or prime will be 6 minus 1 is 5. 5 over 6. Is this clear to everyone?
Yes.
This is how you perform addition rule of probability.
Excuse me, Professor, I want to make a note. Can you like scroll this paper down?
I'll give you 1 minute. Let me see if I can squeeze this for you. All right.
Yes, thank you.
Welcome. I was part A. When you're done, let me know to move part B. The sample space, we're talking about a die. So as you know, a die has 6 faces. 1, 2, 6. That's the sample space. So the sample space got 1, 2, 3, 4, 5, 6. So the number outcomes in the sample space, that's n of s, is 6. Is this clear to everyone?
Yes.
Yes.
Okay. Let's move to part B. Part B. Part B. Part B. Part B here. B. Even or less than 5. Even. Let's use even. Even. It's 2, 4, 6. So n of even equals 3. The second event is less than 5. Less than 5. So that will be 1, 2, 3, 3, 4. So n of less than 5, we got 4 outcomes. Right? Now, do you think these 2 events are mutually exclusive? Do you think they have something in common? You got even.
Or
2, 4, 6. You got less than 5. You got 1, 2, 3, 4. Right?
yes.
So they
2
have
and 4.
2 outcomes in common. So you have even and less than 5. You got 2 and then 2 and 4. So n even and less than 5 equals 2 because you got 2 outcomes. Is this clear? Now let's
Yes.
find the probability. P of even or less than 5 will be P of even plus P of less than 5 minus P of even and less than 5. Okay. Now, P of even is N of even over N of S plus P of less than 5 will be N of less than 5 over N of S minus N of even and less than 5 over N of S. N of even got 3. N of S is 6. Less than 5 is 4 over 6. Minus N of even and less than 5 is 2 over 6. So P of even or less than 5 would be 5 over 6. You see over here? 3 plus 4 is what? 3 plus 4 is 7, right?
Yes.
You see over here?
Mhm.
7 over 6 will give you a number that is greater than 1. As you know, the probability cannot be greater than 1. That's why here you need to remove. That's why I put the minus sign here. Okay? Otherwise, you will be in big trouble here. The probability will be greater than 1. So that's why you need to find the intersection of the two events, which is 2 over 6. Is this clear?
Yes.
Okay, good. Now, the last part C. Are we done? Can we move to part C?
Yes.
Yes.
Huh?
Yes.
Part
I'm
C.
done, Professor.
Okay, part C is what? Part C is 2 or add. Okay? 2 or add. 2 or add. Two or add is just 2. So N of 2 is just 1. Add would be 1, 3, 5 equals 3. So these two events are mutually exclusive events. So why? Because they have no outcome. So event 2, we got just 2. Add, we got 1, 3, 5. So that will give you P of 2 or add. It would be P of 2 plus P of add. You do not need the minus P of 2 or add and add because they have no outcomes in common. So P of add. Okay? So that gives you N of 2 over N of S plus N of add over N of S. That's 1 over 6. And that's 3 over 6. That's 4 over 6. So P of 2 or add would be 2 would be
2 over 3.
2 over 3. Okay, that's how you use the addition rule of probability. Are you done? Hello?
Yes.
You done?
Yes.
Okay, good. Let's move somewhere. Let's talk about conditional probability. So events involving end. In order to use the conditional probability, so some events happen before or will happen, okay? Events involving end. If you're done, let me know.
Good.
Okay. Now, conditional See, in conditional, you see the word condition. Okay? The probability of event B computed on the assumption that event A has happened is called the conditional probability of B given A. Okay? Anytime they give you a problem, you see, they ask for the probability, you see, given an event. So you're talking about the conditional probability. And is denoted the P of, see this is red, P of B given A, okay? P of B given A.
Okay.
When you're done, let me know. And I'm gonna give you the formula to determine the conditional probability.
Me too.
Huh?
I
I'm
heard you.
done.
I said me
Not
too.
yet. Thank you. I'm done.
Okay? This is the formula. Conditional probability formula. The conditional probability of B, see here, given A and is given by probability of B given A, okay? That's the way you're supposed to read this. This is read probability of B given A is equal to P of A intersection or P of A and B over P of A, okay? It's the formula. So here you need to find if the two events are not mutually exclusive. That's the intersection of the two events. All right, so P of A and B. Are you done?
Yes.
Yes.
Okay. I'm gonna show you, I'm gonna solve a few problems here. From the sample space S, you can copy. From the sample space S, 2, 3, 4, 5, 6, and 8, and 9. A single number is to be selected randomly. Given the events A, selected number is odd, and event B, selected number is a multiple of 3. Find each probability. A, P of B, B, P of A and B, and then C, P of B given A. P of given A. So here the sample space has 2 8 outcomes. Are you done?
Yes.
Okay. They give you the sample space 2, 3, 4, 5, 6, 7, 8, and 9. So 8 outcomes in the sample space. Also, they give you 2 events. Event A. Talking about add. Okay, let's look for add numbers in the sample space. That's 3, 5, 7, 9. So there are 4 outcomes in event A. Event B. Selected number is a multiple of 3. Can you, from the sample space, what are numbers that are multiple of 3? What are the numbers are multiple of 3? You got 3. 3 is a multiple of 3 because 3 can divide by 3 evenly. 6 is a multiple of 3. And 9 is also. So n of B equals 3. Got it?
Okay.
Now, look at the 2 events. What do you observe? Do you think they are mutually exclusive events? Yes or no? No. 3
And 9?
and 9. So n of A and B equals 2. Right?
Yes.
Is this clear?
Mm-hmm.
Now,
Yes.
what they asked to find each probability. The first one They ask you to find P of B. P of B will be N of B over N of S. N of B is 2 over 8. N of S is 8. If you want, you can simplify here. That's 1 over 4. That's your P of B. So the two events are not mutually exclusive because they have two outcomes in common. The two outcomes are 3 and 9.
Professor,
Yes,
I'm confused. Isn't N of B equal to 3?
yes, you're right. This is just 3 over 8. Thank you. Done here. So let me just remove this. Thank you. It's 3 over 8. I know I have to do this. Okay. Now they also find P of A and B. P of A and B will be N of A and B over N of S. So that's 2. It's 2 over 8. Simplify. So P of A and B equals 1 over 4. Let's simplify it. Got it? Is this clear?
Yes.
Now, the last part here is part C. Part C, they have to find P of B given A. So that will give you P of A and B over P of A. That's the formula I gave you. All right. We do not know the value of P of A. Let's find out. Determine P of A. P of A will be N of A over N of S. N of A was 4, right? Yeah, 4. That's 4 over 8. Now, of B given A, we found P of A and B before. It was 2 over 8, okay? And then this guy, it's 4 over 8. Now, if you want, you can cancel this. Not this one, sorry. If you want, here you can get rid of the 8. So you got only 2 over 4. So P of B given A, simplifying here, that would be 1 over 2. Got it?
Yes.
Is this clear to everybody?
Yes.
Are you done?
Not yet.
P of A is N of A over N of
Can you
S. N of A, we found that before, was 4.
can
N
you
of S is
please
8. And then P of A and B, we found that before it was 2 over 8 or 1 over 4, but I used 2 over 8, okay? Instead of 1 over 4. And then we found P of A is 4 over 8. So that's why here I cancel the 8. See here I can do that. All right? So we got 2 over 4. You simplify by 2. So the probability of B given A is 1 over 2.
can you please cool it up so I can see, please? Thank you.
Is good?
Yes, thank you.
Welcome.
I'm done.
Try this one. You done?
Yes.
Okay. Given a family with 2 children, so a couple who decide to have children, but just two. Okay. So find the probability that both are boys, given that at least one is a boy. So first, let's solution here. So let let A equals both are boys. No, let's say B instead. Say B, both are boys. And then A, let A be at least one is a boy. One is a boy. Okay? I'm going to replace B with both are boys and A, at least one is a boy. Is that clear?
Yes.
Now, as you know, anytime they have to find the probability here, you need to find the sample space. Now, can someone tell me how many outcomes would you expect in the sample space? How many outcomes?
Two.
Set 2. Determine the sample space. Okay. Let's say here, when you talk about children, it can be girl or boy, right?
Mm-hmm.
Girl or boy. girl, boy, girl, boy. So here, this is first child. So this one is the second child. Okay. Now, the sample space should look like this. So the two people, they try, and then the first one is a girl. The second one can be a girl. So the two children can be girl, girl. Agreed?
Yes.
Or the
Girl,
two
boy.
children can be, the first one is a girl, the second one is a boy. Or the first one is a boy, the second one is a girl, or both are boys. So here, got four outcomes in the sample space. Okay, they try. The first one is a girl. They try again. The second one is a girl. That's my case. I have two girls. I have no boys. Or the first one can be a boy. I'm sorry, the first one can be a girl. See, girl, 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 boy, boy, girl, or boy, boy. Got it?
Yep.
Simple space. Yeah. Now, sorry, give me 1 minute, sorry. Now let's find B. B, both are boys. So B, both are boys. So that would be BB. Yes or no?
Yes.
So NB would be 1. A, at least one is a boy. At least one is a boy. So what does that mean? It can be B, G, G, B, or BB. So N of A will be 3. A and B, let's look for, will be just boy, boy. So N of A and B will be just 1. Right? So look, the two events here, BB, that's B. A is B, G, GB. So they have one outcome in common. Boy, 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 boy. This is clear.
Yes.
Now, so what they ask to find the probability that both are boys. So remember, we use B for both are boys. And we use A, at least one is a boy. So the probability here will be the probability of B, both are boys, given at least one is a boy, will be P of A and B over P of A. Is this clear?
Yeah.
Now, P of A and B would be N of A and B over N of S. And then P of A would be N of A over N of S. So if you want, you can get rid of N of S here. So that gives you get only N of A and B and get rid of N of S. Now you have only N of A and B over N of A. N of A and B, we got found that before was 1. N of A is 3. That's 3. So
Wait, why is N of A and B 1?
it's here. You see it?
Could you explain it?
Okay, sure. Look at this set here and this one here, right? You can
Yeah.
observe they have BB in common. Can you see that?
Yes.
So that's why it's 1.
Okay. Thank you.
Welcome. So that's so P of both are boys given at least one is a boy. Will be 1/3. That's the final answer.
It's not bad. It's just a lot to get there.
Yeah, you know, life doesn't go in straight line. Life goes on broken lines. Yes or no?
Yeah, like a roller coaster.
Yeah. Okay, now, if you're done, we're gonna come back to our PowerPoint. Continue here. It's how you find conditional. Anytime you see the word given, so you are dealing with a conditional probability. Okay? Anytime you see that word. All right. Now, if you're done, let me just move here to here. Now, let's talk about independent event. Two events, A and B, are called independent events if knowledge about the occurrence of one of them has no effect on the probability of the other one. That is, if the probability of B given A equals P of B, or equivalently, the probability of A given B equals P of A. If this happens, the two events A and B are independent. Got it?
Okay.
You're done, let me know. We're done.
Yes.
Let me show you an example. Just give me 1 minute. Okay. A single card is to be drawn from a standard 52 card deck. Given the events, the selected card is an ace. B, the selected card is red. Find P of B. Find P of B given A. C, determine whether events A and B are independent. All right, so again, copy here. So here you can observe got 52 card. So the sample space here is just 52. Are you done? No? Are you still there?
Yeah.
Are you done?
Yes.
Okay. So we talk about code before, right? So the simple space here, we got 52 code. So the number of outcomes is just 52. They give you two events. Code is an ace, okay? So that's A is an ace. Talking about ace, okay, got the ace of heart, ace of diamond, they are red. And we got ace of spade, is black, and ace of, what is the other one again? Oh, boy. Ace of spade. I forgot the other one. Anyone? You got ace of heart, ace of diamond, ace of spade, okay, ace of club. Okay, let me move this thing here. Ace of club. So here you have N of A got 4. Got it? Hello, are you with me?
Yes.
Today people are quiet today. Only one person saying yes. Let me call some names here. Nadia, are you there? Nadia? Not there. Alisa,
Here, Professor.
Strakosana,
I'm here.
Laurieli. Laurieli, are you there?
Yeah, Professor, I was drinking water.
Sana,
I'm here.
El Sionja.
I'm here.
Okay, good. Now, you know, a 52 card deck has 4 aces. You got ace of diamond, ace of heart. Both are red. You got ace of spade and ace of club. Both are black. So therefore, the number outcome and event A is 4. Now, about B. B card is red. So how many red cards do you have in the standard 52 card deck? Anyone? We talked about this last time. Okay, talking about red card, there are 26 red card. 12 are the heart, we got 13. Diamond, we got 13, that's 26. But what I'm going to do here, I don't think I'm gonna give you all. I'm gonna put ace of heart and ace of diamond. And then of course, we got 26. So N of B equals 26. 26. Is this clear? There are 26 red cards. 13 are 13 hearts, 13 diamonds. That's 26. But 2 of them got ace of heart and ace of our diamond. Oh God, we got 7, we got 8, we got 9, 10. But I don't have to give you all the outcomes here. I only give you these 2 because I need these 2 to show you the 2 events are not mutually exclusive events. Okay, so here so A and B will be diamond, ace of heart. N of A and B equals 2. Is this clear? Hello?
Yes, Professor.
You're not paying
Yes,
attention. Maybe
Professor.
so you are doing something else. I'm gonna ask you to open your cameras because you're not gonna ask you to open your cameras because we need to do this together. Okay? Is this clear to everyone?
Yes.
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 Okay.
Yes.
Now, what they ask you to find? Find P of B. Find P of B. So to find P of B, very simple here. P of B will be N of B over N of S. What is N of B? 26. N of S, you get 52. So simplifying here, P of B is 1 over 2. Simplified by then part B, they have to find P of B given A. Right? Now, P of A will be N of A and B over N of S. That's P of A and B. P of A will be N of A over N of S. So if you want here, you can get rid of N of S. So you have P of A even P of B given A will be N of A and B over N of A. N of A and B, we found that before, it was 2 N of A is 4. So P of B given A, simplifying it, that would be 1/2. Now, the last thing they ask you in part C, they ask you if A and B are independent events. Okay? I would say yes. I would say C, yes. They are independent event. Why? Because the probability of B given A is equal to P of B, which is 1/2. Okay, so the two events are independent. Why? Because the probability of B given A equals P of B. Is this clear?
Yeah.
Okay?
Yeah.
Are independent because the probability of B given A is equal to the probability of B. Got it?
Yes.
Let me cover one more thing here in chapter 4. All right. Yes, they are independent events because the probability of B given A is equal to the probability of B. Let's talk about events involving AND. If you multiply both sides of the conditional probability by P of A, we obtain an expression for P of A and B equals P of A times P of B given A. So that's what I'm supposed to get. If the two events are independent, you can replace P of B given A with P of B. So the calculation of P of A and B is simpler when A and B are independent. So if they are independent, you can replace P of A and B. That would be P of A times P of B. Because if the two events are independent, P of B given A is equal to P of B. Got it?
Yes.
Yes.
multiplication rule of probability. If A and B are any two events, then P of A and B equals P of A times P of B given A. If A and B are independent, then P of A and B is equal to P of A times P of
I'm done, Prof.
Yeah, let me show you two simple examples here, and then we take a break. When we come back, I will start chapter 5. Okay? Yeah. Jeff draws balls from the jar below. Okay? He draws 2 balls without replacement. Find the probability that he draws a red ball and then a blue ball in that order. So there are 4 red balls, 3 blue balls, 2 yellow balls. Okay, I wait for you.
All right, good.
Okay, this is very simple here. You don't have to put that down. I will show you the solution in a few minutes, okay? So you have the total ball here. You have I'm gonna show you the solution. Just give me 1 minute. So here you have you have 9 balls. Okay. So here they have to find P of 2 balls. The first one is a red ball. So red and a blue. That's the second ball. So that would give you P of A. So P of O. That's a red ball. It's a red ball times P of blue given is a red. Okay. Now, because this is a keyword here without replacement. Okay. So when Jeff draws the ball, he does not put the ball back in the jar. Is that clear? He does not put the ball back. Are you with me?
Yes.
Yes.
Because of this word, the two events are not independent. Okay? Because he put the ball back are not independent. So very simple here. What we're going to do here, how many red ball do you have?
4,
4 over what?
9,
This is the red ball, right? Times the second ball is a blue ball. How many blue ball do you have?
3,
Over what?
9,
what? Hmm?
9. No, 8 because you didn't put it back.
Very good. So here should be over 8 because suppose it shows this red ball here, okay? All right, that's the first ball. So how many we got left? We got 8. So it should be 3 over 8 because it's not put the ball back. Is this clear? Got 4 red over the total ball. Got 9 balls in total. And then also the second ball is a blue ball. This is the first ball. That's the red ball here. The second ball is a blue ball. But once you draw a ball, you cannot put the ball back in the jar. So here, this is the red ball. You got 8 left. Okay. So is this clear to everyone?
Yes.
Let me show you the
Yes.
solution
Yes.
here. There you go. Okay. The probability the first ball is a red ball. That should say R stands for red. That's the first ball. And the second ball is a blue ball. All right. So that's P of R1. That's the first ball. Two events are not independent. So that's 4 over 9 times 2 over 8. So that's 1 over 6. Got it?
Yes.
Got it.
And so the two events are not independent because they put the ball, sorry, they did not put the ball back in the jar. If they put the ball back in the jar, the two events are independent. Okay? You're done.
Yes.
Okay.
Yeah.
So same problem here, but there's just a difference here. The difference is this. This time with replacement. Okay? With replacement. Before, without replacement, the two events are not independent. Now, with replacement, the two events are independent. Okay? So here, that will give you very simple here. Same thing here. So that'll give you P of red. That's the first ball. And P would be P of O1 times P of B2, because the two events are independent. Red ball, got 4 red ball, that's 4/9. You got 3 blue ball, but over 9, because you put the ball back, that's the difference. So here that would give you, let me see here, 4/27. So here the two events are independent. Is this clear?
Yes.
Let me show you the solution here. It's okay. I'm gonna show you the solution. Here you go. Because the ball is replaced, repetition are allowed. In this case, event B2 is independent of O1. All right. So let's take a it's 7:38 now. Let's take a break. We will resume at 7:50. Okay.
Okay.
All right, 7:50.
Thank you.
Welcome. So in order arrangement of objects, okay? There is order. In time we talk about permutation. Order is important. Order does matter, okay? So the number of different permutation of n distant objects is n factorial. This symbol, when you see this, is read n factorial. It's just a number. All right? So n factorial is equals to n times you decrease n by 1, by 2, by 3, and so on. Okay? For example, if you have 5 factorial, just a number here. See, 5 factorial. 5 factorial is 5. You subtract 5 by 1, that's 4. Subtract 4 by 1, that's 3. Times 2 times 1. And then you multiply them, that's 120. It's just a number. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. That's 720. That's okay? Answer. Is this clear?
Yes.
You're done.
Yes.
Yes.
Now, when you see 0 factorial is 1. 1 factorial is also 1. 0 factorial is what? 1. It's just something you need to accept. All right? To prove this, you need to take a course I took when I was in graduate school. To prove 0 factorial is 1. All right? But just anytime you see 0 factorial, replace 0 factorial with 1. Is that clear? Hello?
Yeah.
0 factorial is what? Hello?
Yes, Professor.
We need to work here together. When I need to hear your voice. Okay. I show you this example before. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, that's 720. 4 factorial is 4 times 3 times 2 times 1 is 24.
Got it, Professor.
Okay. Now, let me show you something here. Let me show you an example here. Suppose you have 6 factorial over 3 factorial. What is 6 divided by 3?
2.
2. What is 6 factorial divided by 3 factorial?
2
No.
factorial?
That would be wrong. It's more than that. 6 factorial over 2 factorial. Okay, let me just put this up there.
Oh, I see. I got it. I see. So
Is
3
not equals to 2 factorial, okay?
2 times
So what can you
1.
do here? You can take 6 times 5 times 4, and then you stop at 3 factorial.
Oh.
And then you simplify.
Okay, why in the example it goes all the way down to 2 and 1?
Yeah, that's you see the 6 factorial here?
Yeah,
See this number here?
yeah.
Let me show you. Now, when you have 6 factorial, we can go all the way down to 1. That's why we're trying to show you here, okay?
Mm-hmm.
Got it?
Mm-hmm.
Now, if you have 6 factorial over 3 factorial, you can go all the way down here to 6 times 5 times 4 times 3 times 2 times 1, and then 3 factorial can be 3 times 2 times 1.
Mm-hmm.
And then what can we do here? We simplify. You see here, simplify the 3, simplify the 2,
Oh, I see. Okay, I get it.
simplify the 1.
Okay.
And then you have only 6 times 5
Times 4.
times 4. Okay, 6 times 5 times 4. So that gives you 30. That will be 120. Okay, that's 6 factorial over 3 factorial. But you cannot say 6 factorial over 3 factorial is 2 factorial. That's wrong. Because 2 factorial will be 2 times 1, which is 2. But here, you can observe it's not 2. It's just a big number. It's 120. Got it?
Yeah. Gotcha.
Now, another way you can do that, if you have 6 factorial over 3 factorial, you don't have to go all the way down to 1. You can stop. All right, give me 1 minute. Okay? Can go all the way down to, I'm gonna stop at 3. Because the bottom number here is what? Is 3 factorial. And then I cancel the 3. See here, I still get 6 times 5 times 4. Is this clear?
Yeah.
If the
Yes.
bottom number were 4 factorial, I would stop at 4 factorial. If the bottom number were 5, I would stop at 5 factorial. Is this clear?
Yeah.
Got it? Okay. Now, let's continue here. So the objective of a 9 times 9 Sudoku number puzzle is to fill the grid so that each row, each column, and each 3 times 3 grid contains the digits 1 to 9. How many different ways can the first row times 9 Sudoku grid be filled? This is just a 9 factorial here. Okay, that's the answer. So the number of permutation is 9 factorial. So that will give you 362,880 ways for this different way. And different way is the first rule of the blank 9 times 9 so that could be filled. Okay. 9 factorial.
Okay.
You're done.
Yes.
Yes.
Let's continue here. Okay.
Yeah.
The formula you need to use to find the number of permutation is this formula. NPR is n factorial over n minus r factorial. So keep in mind, anytime you talk about the permutation, order is important. Okay. Now, n always greater than greater or equal to r. Okay. N all cannot be greater than n, but they can be equal. But n is always greater than or equal to r. Got it?
Okay.
You're done.
Yes, Professor.
All right, let me show you some examples how you can calculate the number of permutation. Very simple. Find the number of ways of forming 4-digit codes, okay? And which no digit is repeated. So when you talk about the 4-digit code here, can be 1, 3, 5, 7. It's a 4-digit code. Make sense? Because it said no digit is repeated. It can be 3, 0, 4, 5. Got it? But you need to know
Yes.
again form. Now, how many digits are there? How many digits are there? How many?
4.
Hmm?
4.
No. You need to choose among the digits 4. Okay, so here they give you or equals 4, but n equals 10. Why I said 10? Because there are 10 digits. When you talk about digits, talking about number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, they are digits. Is this clear?
So, Professor, it should be single digit?
Anytime you talk about digits, the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 digits. That's why n is 10.
Okay, thank
You're going to choose among the 10 4. So you need to know meaning, okay? Very simple here. What you're going to do here, you're going to use permutation because you cannot repeat a digit, okay? So that you use permutation here. NPR is n factorial over n minus r factorial. What is n? N is 10. What is r? R is 10. R is 4. Okay?
Okay.
Got it? And then you solve this. So let me just show you the solution here. So you need to select 4 digits from a group of 10 because you got 10 digits. Anytime you talk about digits, talking about 0 through 9. Okay? So n is 10, r is 4. So that's 10 over 10 factorial. 10 minus 4, that's 6 factorial. Watch. They go all the 10 factorial, they start at 10, and then they go all the way down to 1. Can you see that? And
Yes.
same thing for the 6 factorial. Start at 6, you go all the way down to 1. And then you simplify 6, 5, 4, 3, 2, 1. And then you just put this there for you. So here, this will give you 10 times 9 times 8 times 7. Okay? And then you multiply 10 times 9 times 7. So that's 10 times 9 is 90. 90 times 56 is 5,040 ways. So there are 5,040 ways you can form a 4-digit code. Okay? With no digit is repeated. So that means a 4-digit code, if you have something like this, 1, 3, 1, 4, that's not good. Why is not good? Why this one is not good?
Because they're two of the same number?
Because we can repeat the number.
Which number here you repeat? 1.
One.
One.
Okay? So therefore you cannot repeat. So later on you cannot use a different formula if you want to repeat a digit. Okay? That permutation. Okay? Got it?
Got it.
Yeah.
All right. "43 race cars started the 2007 Daytona 500. Okay? 43. Okay? So that's N. N equals 43. You see here, this guy here is 43. That's N. This is N. How many ways can the car finish first, second, and third? So what is the value of R? Hello, I mean, N is 43. Do you agree with me?
Yes.
How about or? Or will be first.
First, second,
Second.
third.
Or is 3, right? So here
Yes.
there is order. So therefore, we're going to use permutation. Why I said there is order? There is a first, there is a second, there is a third. So order. Got it? Order. First,
Yes.
second, or third. Now, if they said two cars finish first, so here there is no order here. Can you see that?
Yeah.
So here there is order. There is a first, like I don't know. In the United States, there is a president, right? There is a vice president, and there is someone else. I don't know. All right. The president is first order. The vice president is second. Or the secretary of state is third. I don't know. Or the defense secretary is fourth. Here there is order. All right.
Gotcha.
Good. Now, so N is 43. So you need to select 3 cars from a group of 43. Why you use permutation? Because there is order. There is the first, there is second, there is the third. So here you have 43 cars, 3 taken at a time. All right. So that's 43 factorial over. Remember the formula I gave you for is the formula is this. It's NPR is n factorial over n minus r factorial. Okay? Replace n with 43, or with 3. You get 43 minus 3 is 40. And then here, if you, let me add this for you. Start at 43, you go down 42, you go down 41, and then you stop at 40 factorial, because you got the 40 factorial below, and then you simplify 40. That's why I got 43 times 42 times 41. So when you multiply these 3 numbers, you get 74,046 ways. Got it?
Yeah.
Good. Now, let's talk about distinguishable permutation. The number of distinguishable permutation of n objects where n1 are of one type, n2 are of another type, and so on, is given by this n factorial over n1 factorial times n2 factorial times n3 factorial times, if you got more type, you times that nk factorial. Keep in mind, n is the sum of n1, n2, n3, n4, and so on. Okay?
Okie doke.
All right, are you done?
Not
Yeah.
yet, Professor.
Thank you, Professor. I'm done.
Okay, let me show you an example. So a building contractor is planning to develop a subdivision that consists of 6 one-story houses. You can take notes. 4 two-story houses and 2 split-level houses. And how many distinguishable ways can the houses be arranged? When you're done, let me know. Are you done?
Yes.
Yes.
Yeah.
So this is very simple here. So this is N1, okay? This is N2, 4. And then this is N3. So can someone, what is the value of N here? N would be the sum of N1, N2, and N3. That's what it, let me go back to this thing here. See? N1 plus N2 plus N3 will be N. So now N1 is 6, N2 is 4, N3 is 2. So N, there are 12 houses and the subdivision. N equals 12, N1 is 6, N2 is 4, 6 plus 4 is 10, 10 plus 2 is 12. So that will give you 12 factorial over N1. N1 is 6, 6 factorial, N2 is 4 factorial, and then N3 is 2. And then when you do this calculation here, let me just show you, I can do this here. So what we're going to do here, we're going to take 12 times 11 times 10 times 9 times 8 times 7, and then stop at 6 factorial. Why we stop at 6? Because 6 is greater than 4. So 4 would be 4 times 3 times 1. 2 would be 2 times 1. Now we can show the 6. Okay? Now when you multiply the top, you're gonna get a number. When you multiply the bottom, that will give you 24 times 2, that's 48. Multiply the top, that will give you a number over 48. So when you do the division, you get 13,860 distinguishable ways. Is this clear?
Yes.
Yes.
Okay. That's how you use distinguishable permutation. Right? Let me show you another example. Determine the number of distinguishable arrangements of the letters of the word initially. Okay? B, Mississippi. I wait for you. Are you done?
Yes.
Okay.
Yeah.
You see the first one, part A. You see the word initially, right? How many letters you have in this word?
Eight.
Are you sure it's 8? How many letters you have in initially?
9.
9, right? So the total number here, let's put n equals 9, right? Now look at the word. You can observe letter I. How many ICs you see there?
3.
3. So N1 is 3. About L?
2.
2. N1 is 3 because we got 3 ICs. N2 is 2 because we got 2 L's. So here that will give you n factorial over n1 factorial times n2 factorial. That's 9 factorial over 3 factorial times 2 factorial. And then you do this calculation here. So is this clear?
Yes.
Yes.
Let me show you the solution now, because you have an idea here. Why n is 9? Because you got 9 letters in the word initially. Why n1 is 3? Because you got 3 ICs. N2 is 2. Why N2 is 2? Because you got 2 L's. Okay? So let me show you the solution here. Now you have an idea now. See? 9 letters total. So that's 9 factorial. 3 ICs and 2 L's. So that's 9 factorial over 3 factorial, 2 factorial. So when you do this calculation here, you can go all the way down to, you stop at 3 factorial, okay? If you want here, you can do that. You can go here. 9 factorial would be 9 times 8 times 7 times 6 times 5 times 4. And then you stop at 3 because 3 is greater than 2. Then times 2 factorial. Then you can show that. And then you multiply the tops. That will give you a number I do not know. And then you divide that number by 2, because 2 factorial is 2 times 1, which is 2. The 0, 8, 4, 0, 6 over 2. Okay?
Okay.
Now, B, Mississippi. Okay? Got that word. Mississippi. 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 This is the word, all right? Mississippi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So Mississippi, this word has 11 letters. Yes or no?
Yes.
How many S's you have?
4.
How about I's?
4.
4. How about P?
2.
Okay. So here, I'm sorry, let me solve this for you. Sorry. Mississippi. I give you 1 minute. Let me just move. There's something here. All right, Mississippi. N equals 11. N1 equals 4 issues. N2 equals 4 I's. And then N2 equals 2 P's. Okay? So that gives you 11 factorial over 4 factorial times 4 factorial times 2 factorial. So 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. So you're going to cancel one of the 4 factorial. And so one of the 4 factorial here. So you have 11 times 10 times 9 times 8 times 7 times 6 times 5 over 4 factorial times 2 factorial. You multiply the tops, so 4 times 3 times 2 times 1 times 2 times 1. So just multiplying the tops. So it's 11 times 10 times 72 times that's 1 6 6 3 2 3. Divided by 48. So then she'll give it 34,650. Okay, 34,650 different ways. You can arrange the word Mississippi. Got it?
Okay.
Mississippi. So you see my first name, Jean, is just 4 factorial. All right, show you here. My first name is Jean. How many different ways? That'll give you just 4. Now you can observe no letter repeats. So that will be just 4 factorial. So 4 factorial will give you 24. So my first name, there are 24 different ways I can arrange my first name. Got it?
Got it.
Got it.
It can be, let me show you here. If you want, Jean. Okay. Jean. So that would be 4 factorial. 4 factorial is 4 times 3 times 2 times 1. That's 24 different ways. So it can be, my first name can be Gan, can be Ge, can be Jana, can be
I don't think it makes more names than that.
okay, it can be Giant, it can be Jin, can be Jn, can be Jne6, or it can be Ajn, Aanj, or it can be Enaj, Eanje, or it can be Ej, A, N, A, J, N, A. Or it can be N, A, E, J, N, A, J, E, N, E, J, A, N, E, A, J. Can be N, J, A, E, N, J, E, A. Or it can be stick A now. A, E, N, J. A, E, J, N. A, J, E, N. A, J, N, E. Or it can be A, N, E, J. Or A, N, J, E. That's 24 different ways. Okay?
Okay.
Now, let me see here. If I take the name of Sanaa, see here. Sanaa is S-A-N-A-A. So here, that's N equals 5 here. So that will be just 5 factorial over 3 factorial. Okay? So Sanaa, we have 5 letters in this, okay? 5. But here I observe I got A 3 times 1, 2, 3 over 3 factorial. So I believe Sanaa can 20 different ways. That would be 5 times 4, start at 3, 5 times 4 is 20 different ways. Okay, Sanaa?
Yep, makes sense.
Let me see, Darieli. See here, Darieli, no letter repeats here, and see 2, 4, 7. So that gives you 7 factorial. 7 factorial, that would be 720 times 7. 720 times 7. So now really, your name can be arranged of 5,040 different ways. All right, Agili. You see the name of LC Monjua, same thing here, 7 different ways. Sorry, 7 factorial. That gives you 5,040. All right, good. All right.
Mine's 8.
Is 8?
Yeah.
Yeah, that's true. So no letter repeat. Wow. Okay. 40,000 create 20 different ways. Okay.
Oh my God.
All right. Good. My last name, it's Phanor, 6 different ways that give you 720 different ways. My last name. No letter repeats. Yeah. All right. Good. Let's continue here. Let's talk about combination. Combination, the formula here. The only difference here, you multiply by all factorial. You take the same permutation formula here, you add this thing here, you multiply by this here. That's the only difference here. See here, this guy. All right. But here, when you talk about combination, order is not important. Okay, that's what he said here. A selection of all objects from a group of n objects without regard to order. So here order is not important, okay? Permutation order is important. It does matter, but combinations order is not important, okay? It does not matter, all right? That's the only difference here.
Okay.
Suppose we need to calculate C7C2, okay? N is 7, O is 2, so that gives you 7 factorial over 7 minus 2 factorial times 2 factorial, okay? Got it? Now, let's simplify here. So here you get 5 factorial below here, because 7 minus 2 is 5 over 7 factorial. Take the 7 factorial, you go all the way down, then you stop at 5. 2 factorial is always 2. And cancel this thing here. So that's 7 times 6 over 2. 42 over 2 is 21. So 7C2 is what? 40? 41. It's 21. Is this clear?
Yes.
Right? So keep in mind, combination order is not important. Order does not matter. So it can be in a way, so you can have two people finish first, 2 people finish second. So there is no order here. Okay? Is this clear?
Yeah.
All right. So let's continue here. Let's try here. So a state Department of Transportation plans to develop a new section of interstate highway and receives 16 bids for the project. Okay, 16 bid for the project. So that's N. The state plans to hire 4, that's all of the bidding companies. How many different combinations? See here? So here you cannot use permutation here. So here you must use, I'll give you 1 minute, please. So here n equals 16, or equals 4. So here that would be 16C4. Okay, so 16C4. When I use the combination, not permutation here. That's why they asked you here. They said, how many different combinations of 4 companies can be selected from the 16 bidding companies? Is this clear?
Yeah.
Yeah.
And I just use the formula. N is 16 or equals 4. Or equals 4. Okay, so you need to select 4 companies from a group of 16. N equals 16 or equals 4. Order is not important. Okay? Order is not important. Are you done?
Yes.
Now
Yes.
just, huh? Someone said no.
Yes. Yes.
Give you a few minutes. Are you done now?
Yeah.
Okay, so that's 16C4, all right? N is 16, or is 4, 16 minus 4 times 4 factorial. 16 minus 4 is 12. Now you go all the way down to 12 because 12 is greater than 4, and then you simplify the 12 factorial. The 4 factorial is 4 times 3 times 2 times 1. When you multiply these numbers, you're gonna get 1,820 different combinations. 1,820 different combinations. Is this clear?
Yeah, this is good.
Okay. Try this one. TEDI Student Advisory Board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve any of the positions. What is the probability of selecting at random the 3 members that hold each position? Okay, I don't think you can solve this problem. So Are we done?
Yes.
Okay. So there's only one favorable outcome here. So we got this 17 members. Let's come back here. 17 members, 3 members serve. So that's a permutation here. Why is permutation here? Because there is what? Order. See
Order.
here? Board chair, that's the first guy. Secretary, that's the second guy. And the third guy is webmaster. Is this clear? So here you use what? Permutation. Is this clear?
Yeah.
Good. Now, they ask you what is the point of selecting at random the 3 members that hold each position. Here you go. First, you find there's only one favorable outcome. There are 17 members. You select 3 among 17. So that gives you 4,080. Ways the 3 position can be filled. Okay. Now, what is the probability? Let me just read for you.
Done. I took a picture.
Okay. Now you need to select the 3 members. Okay. The 3 members, and each can be either the webmaster, either the board chair, or the secretary. That's 1 over 4,080. So that's approximately 2 times that will give you 0.0002. That's the probability here. Okay.
Got it.
All right. I think we just solved. We solved this problem earlier. We solved this. All right. So suppose you have 11 letters consisting of 1 M, 4 ICs, 4 S, and 2 Ps. If the letters are randomly arranged and order, what is the word that the arrangement spells the word Mississippi? Okay. There's only one variable. 11 factorial, that 1, 4 factorial, 4 is before, and that would be 1 over 8. Okay, same thing. All right. So that's set here for chapter 4. All right. So let me just start chapter 5. I don't know, it's up to you. If you want, you can stop here, or we can continue with we can start chapter 5 next week.
I think a good digestion of this information would behoove our learning abilities.
Chapter 5 is about probabilities. Right? That's why I told you earlier, probability is not easy. So students always fail that test when they took a test. All right, but that would be online, so we have plenty of time to solve the test. Okay, now, so I'm gonna stop here. Okay.
Thank you.
I'm gonna stop here. when I meet you next week, I will start chapter 5. Okay?
Sounds
So before I let you go, is there anything you need to ask?